Hello everyone, Jai Hind and good morning. Welcome back to the platform of PMF IAS. This is the second class and today we'll be going to discuss about Earth. Sonali, good morning. Who else is here? Please type in the message and let me know that you're watching this session live. And as well, we'll be talking about Earth, the evolution, origin of the Earth in today's session. And we'll be also talking about the interior of the Earth today itself. All right. So we'll be covering all this. I hope what we studied yesterday, that is the universe as well as the solar system, is clear to everyone. If you have any doubt, you can ask your doubts right now. Okay, no doubts. So let's move forward and let us discuss Earth as a whole, or we'll be discussing the formation as well as the interior of the Earth today. All right, let me share the screen with you. Just a second. All right, guys. So today we'll be talking about the origin as well as evolution of the Earth in today's session. Now, the origin and evolution of the Earth is linked to the origin of the solar system itself, because as the solar system emerged, that is when we had the emergence of the Earth itself. So when we talk about evolution and origin of the Earth, our Earth originated with the solar system about 4.5 billion years ago. Now, although in the previous times, all right, in the earlier eras when we do not had that much of scientific knowledge, at that point of time, the origin of the Earth was linked to various myths as well. All right. So the Hindus, they considered the Earth to be half of a golden egg, which was balanced on the back of a turtle with the help of four elephants. In the same way, ancient Egyptians, they visualized the Earth as a floating sphere in the sea. And the Polynesians, they thought that the Earth, it began like a egg. It is an egg that is floating in the sea. So that is what the Polynesians, they thought about the Earth. However, with the passing of time and with the advancement of the knowledge, scientific knowledge, we came to know that the Earth was formed along with the solar system after the sun was formed. And yesterday I told you that for this, there is one particular hypothesis that was put forward, and that hypothesis is nebular hypothesis. In 1950, Otto Smith in Russia as well as Carl von Weizsäcker in Germany, they revised the nebular hypothesis that was given by Kent and Laplace. Both of them, Kent and Laplace, they gave the gaseous and nebular hypothesis. Later on, this hypothesis, nebular hypothesis, was revised. And they said that the sun was made by a nebula. There was a solar nebula. We have studied yesterday about the formation of the stars. So stars are formed by the nebula. What is nebula? I have told you yesterday also. Nebula is nothing but it is the cloud of gases and dust particles. So there were gases and dust particles, and this nebula led the formation of our sun. So this nebula consisted mainly hydrogen and helium and dust particles, and when there was gravitation, the friction and collision of the partition that led to the formation of a disc-shaped cloud that is called as accretion disk. It is known as accretion disk, and later on the planets were formed through this accretion disk itself. So how our solar system came into being? What is revised nebular hypothesis? It says that initially there was a nebula. This nebula is nothing but it is the nebula of our sun, which led to the formation of the sun. Now, due to gravity, what happened? That this nebula started getting concentrated, and most of the mass got concentrated in the center. That led to the formation of the sun. It led to the formation of our sun, and at the same time a disc-like structure was formed around the sun. This disc-like structure is called as accretion disk. It is called as accretion disk. And as the gravity increased in the accretion disk, that led to the formation of the planets. All the planets that we see today, the 8 planets of our solar system. And that is how our solar system or our Earth came into being. So over here you can see how this all happened. So there was a spherical, roughly spherical, slow rotating nebula, and out of gravity it contracted. After the contraction, what happened? A rotating disk was formed in which the middle size or middle mass was concentrated, and that led to the formation of proto-sun or proto-star, that is our sun. Later on, this slowly and slowly out of gravity, this coalesced, and as it coalesced, that led to formation of planetesimals. Planetesimals are basically kilometer-sized chunks. Later on, what happened was, due to collision of these planetesimals, a giant outer planets were formed, which were basically gases, and the terrestrial planets were formed, which consisted of solid crust. And this has been proved. This has been proved, as you can see over here. This is a picture that was taken by NASA. All right, NASA, this picture is credited to NASA. And over here, you can see that there are still those remnant of the accretion disk. Over here, you can see they are dust particles. They are still dust particles, gases. They are still revolving around the sun in the form of a belt, and within these belt you will find the planets which are located. So this is how the solar system came into being, or our Earth, it came into being. So this is here again, once again you can see over here in this picture that there was core collapse in the form of molecular cloud. Then it resulted into formation of proto-sun in the center and a circumstellar disk or an accretion disk. There was accretion of the planets, and present day solar system came into being. In the form of Earth, how our Earth came into being? So there was pebbles, and these pebbles formed planetesimals when they joined together. These planetesimals gave result to the proto-Earth or the earliest Earth, and there was Theia. I told you this was a planet that was coming close to the Earth, and there was giant impact which led to the formation of moon along with the Earth. And later on, the different layers were formed in the Earth, which we will study in today's session itself, the internal structure of the Earth. All right. This is how moon came into being after the impact of the Theia. This is called as giant impact, and this giant impact led to the formation of moon, which is the only satellite, only natural satellite of the Earth. Now, what happened was, after the Earth was formed, so Earth was already, it was very hot. It was very hot. The Earth was at that point of time. And what happened was, due to the gravitational differentiation that happened at that point of time, iron, which is heavy element, it started to sink towards the center. And the lighter material, they floated upwards. And that resulted into formation of the layered Earth structure that we see even today. So today we know that the Earth is comprised, or Earth consists of 3 different layers internally, that is crust, mantle and core. So these different layers of the materials, they were formed because of the gravitational differentiation, as well as when the iron, it started sinking towards the center, that released potential energy which melted the entire Earth, and later on, as the Earth cooled down, it led to the formation of the structured layer of the Earth. All right, so you can see over here iron and then lighter matter. So lighter matter, it moved towards the upward areas. Now, when we talk about this phenomena where the iron, due to gravitational differentiation, it moved to the center, this process or this phenomena is also called as the iron catastrophe. This is called iron catastrophe, where the iron moved towards the center due to the gravitational difference. All right. Now, as we have different periods, all right, we have different periods and we measure the time period using different methods. We use seconds, we use hours, we use minutes, as well as we use months and the year. In the same manner, the earth was formed 4.5 billion years ago. And during that point of time, year by year analysis is not possible. So we have divided the complete age of the earth into different periods. These periods are called as super eon. Then within the super eon, we have eons. In eons, we have eras, then period and epoch. So this is the different time period where different processes or different phenomena were occurring on the Earth's surface. And that is how we calculate the age of the Earth or the geological time scale. What is geological time scale? When different things happened on the Earth. The first super eon was Hadean. Hadean, it was from 4540 to 4000 million years ago. That led to this is the time period when the formation of the earth happened, as well as this is the time period when the formation of moon happened. Later on in the Archean period, in the Archean super eon, what happened was the earth crust, it had cooled enough so that formation of continents started, or the formation of continents happened, and also life started to form in the form of there is eukaryotic and prokaryotic bacteria. So prokaryotic bacteria without nucleus, they formed during the Archean period. Later on in the Proterozoic period, bacteria, algae and jellyfish, they occurred, or they, emerged on the surface of the earth. So this is the period, this is the time period where the life was forming on the earth. The earth formed as well as the life was beginning on the earth during this point of time. So Hadean period and Hadean eon, what happened was between 4.5 to 4 billion years ago, formation of the moon as well as the formation of the earth happened. We had the formation of moon, we had the formation of earth, and it also led to late heavy bombardment. What is bombardment? That the different asteroids, they came into contact and what they did was that they bombarded earth during this point of period, and that led to asteroid impacts as well as extreme volcanism. There was no oxygen at that point of time. When the earth emerged in the early periods, there was no oxygen. It was devoid of oxygen. It was only afterwards that the life form existed. They started photosynthesis, that the oxygen was formed on the earth. All right, so there was no oxygen at this point of time. Later on, the earth, it cooled down to form the solid crust, and at this point of time, the earth had temperature of about 230 degrees Celsius. There was carbon dioxide that was found heavily in the atmosphere, and the oceans were created during Hadean eon. Ocean water, it recovered or removed most of the carbon dioxide from the oceans. It absorbed the carbon dioxide, and that led to formation of the oceans, and during this point of time, there is no proof of life. Later on, Archean period or Archean eon happened during the Precambrian period. So over here, cyanobacteria emerged. The cyanobacteria, which were the first bacteria, they emerged during this point of time, and there is the earliest fossil evidences which are found over here. During this point of time, only prokaryotes were there. Who are prokaryotes? Which have no nucleus. They have no nucleus. So those bacteria are called as the prokaryotes. So there was such type of bacteria that emerged. Again, there was no oxygen and the atmosphere was at this point of time also comprised of carbon dioxide and the other greenhouse gases. Formation of continents began during this point of time. This point of time, Earth was still hot, so there was lot of volcanism as well. Oceans became acidic, and at the end of this Archean period, plate tectonics, it was similar to that of the present. The plates, they started emerging and they started forming. Then in the Proterozoic eon, which is still in the Precambrian period, bacteria emerged which started producing oxygen. And it is at this point of time that the oxygen emerged on our land surface. All right. Eukaryotes were formed along with some other soft-bodied multicellular organisms. There was extensive glaciation and it resulted into snowball Earth. There was drop in sea level and glaciation occurred. Tectonically, this was very active period and supercontinent cycles started at this point of time with the dominant supercontinent that was Rodinia. And the modern orogeny, what is orogeny? It is the mountain formation. Formation of the mountains began at this point of time. So there was formation of mountains as well as the present orogeny, it started, or the modern orogeny, it started beginning at this point of time. All right. So this was Precambrian era. Later on came the Paleozoic era. In the Paleozoic era or the Ordovician eon, there was Cambrian period. Before Cambrian, there was Precambrian. But in the Precambrian, we have three different eras or eons: Hadean, Archean, and Proterozoic. Then came the Paleozoic. In the Paleozoic eon, we have Cambrian period. In the Cambrian period, what happened was that invertebrate animals which do not have the spine. What are invertebrate animals? They are the animals which do not have spine of themselves. They emerged at this point of time, like first fishes were there, brachiopods, trilobites, as well as the chordates appeared during this point of time. Then came Ordovician. In the Ordovician, early bony fishes occurred as well as diversification of animal life began. Still, there was no land animals. In the Silurian period, first land animals emerged and first vascular plants emerged during the Silurian period. Later on came the Devonian period. In the Devonian period, first seed plants emerged and it is also known as Age of Fishes. Please remember this. This has been asked in the examination. Which of the period is called as Age of Fishes? So you must remember that it is Devonian period which is called as the Age of Fishes, and first amphibians emerged on the Earth's surface. Later on, we have Carboniferous period. During Carboniferous period, there were two different periods, Mississippian and Pennsylvanian. There was seed that were formed during this form of time, seed ferns, and the first insect as well as trees emerged during this point of time. And after the mass extinction, these trees led to the formation of coal. That is why it is known as Carboniferous period, because the trees, when the fossils were formed, and later on these trees, they led to the formation of coal that we see today, and that is why it is called as it is known as the Carboniferous period. Later on came the Permian period. In the Permian period, there were first reptiles that emerged on the earth, and there was major extinction. And this major extinction and also the trees that happened over there that they emerged on the surface of the earth, that led to the formation of the coal that we see majorly today. So this was Paleozoic period, Paleozoic eon, and in the Paleozoic eon we have Cambrian, Ordovician, Silurian, Devonian, Carboniferous and Permian periods. All right, so this was after the Precambrian era or the eon. Later on came Mesozoic era or Mesozoic eon. In the Mesozoic eon, we have three different time periods. We have Triassic period, During Triassic period, dinosaurs emerged, and this is called as the age of reptiles. The age of dinosaurs is Jurassic period. You must have watched Jurassic Park in your childhood, right? So Jurassic Park, basically the name of that movie is because that was the age of dinosaur. During Jurassic, the complete earth was covered with with the dinosaurs. Even the first birds emerged during Jurassic period. But again, this is a question of the examination, that in which period dinosaurs became extinct. So it was during the Cretaceous period that extinction of dinosaurs happened. Most of the students, they mark Jurassic period because with dinosaurs they connect Jurassic Park, the movie that was basically on the dinosaurs. But Jurassic is the age of dinosaur. After Jurassic came Cretaceous period, when there was extinction of the dinosaur and first primates occurred, first flowering plants were formed or they emerged on the earth. So this was Mesozoic era after Paleozoic era. All right. Later on came the Cenozoic era. In Cenozoic era or the Anthropocene eon, we have two different periods, that is tertiary period. During tertiary period, rise of mammals happened, as well as it is also known as age of mammals. And later on, right now we are in quaternary period. In quaternary period, we had the rise of humans. Again, the tertiary period, it is further divided into Paleocene, Eocene, Oligocene, then Miocene and Pliocene. And quaternary period is divided into two different era, that is Pleistocene and Holocene. Holocene is the most recent where we are right now. So we are in the Holocene period at present. So this is how we see what different types of changes occurred on the earth on the basis of the different time period, and these different time period we call it as geological time scale of the earth. When this all thing were happening, the earth, it basically went through different phases of ice ages. There were different ice ages that happened on the earth during this point of time when the earth was getting formed and the different life forms were emerging. The first of the ice age happened during the Precambrian period. During the Precambrian period, and this was called as Huronian ice ages. Then later on, second ice age also came during this point of time, Cryogenian ice age. Then came the Paleozoic era. In the Paleozoic era, India Saharan ice age happened and Karoo ice age happened. All right. And later on in the quaternary period, and most importantly, in the Pleistocene period, the ice age happened in the Pleistocene period or epoch. And during this Pleistocene period, in the quaternary period, we had quaternary glaciation that happened, and there were four glaciations. Please, you have to remember these names. The name are Gunz, Mindel, Riss, and Worm, and they happened in the same chronological manner. The first ice age during the quaternary period is called as Gunz. Then there was Mindel, then Riss, and then Worm. Again, in your examination, the chronological order can be asked. So you have to remember the chronological order of these ice ages. So how many ice ages happened on the earth right from the starting? So there were in total how many ice ages? Total 5 ice ages happened. There were total 5 ice ages that happened: Huronian, Cryogenian, Andes-Saharan, and also Karoo ice age, and then quaternary glaciation. In the quaternary glaciation, we had 4 different periods of ice ages: Gunz, Mindel, Riss, and Worm. Also, there were mass extinctions. In total, there had been 5 mass extinctions as of today. All right. What is mass extinction? Where the different species, we have lots of species, so there is a sharp spike in the rate of extinction of those species, and these is caused by a catastrophic event or rapid environmental change that led to the 5 mass extinction in the Earth's history. So the first extinction was Ordovician Silurian extinction. It was 440 million years ago. So during this period of time, a glaciation event happened. Also, there was a heating event that happened. So there was a glaciation, then later on there was heating, and during this point of time, the plants were already emerged, the plants were there. They removed carbon dioxide from the air that resulted into global cooling as well as glacier formation. When the glacier were getting formed, you must have seen that the volume of ice drop. When the water, it changes into ice, its volume or its, the height, it drops. So there was drop in the sea level, and that resulted into reducing habitat. Then came global warming and sea level rising again. So at this point of time, 86% of the life was lost. So this was Ordovician Silurian extinction, the first mass extinction. Later on came late Devonian extinction during 365 million years ago. And during this point of time, about 75% of the life that died during late Devonian period. So over here, what it says that, because of the plants that were emerging. So the plants had deep roots that released lots of nutrients into the oceans. And later on, that nutrients led to eutrophication. What is eutrophication? When the nutrients level rises. So when the nutrient level rises, what happens is algae bloom happens, because algae depends on the nutrients. And because of this algal blooms, what happened was maximum of the oxygen was consumed by the algae. That resulted into suffocation of many species, and that resulted into late Devonian extinction that happened majorly in the oceans. Also, there is another theory as well which suggests that there was global cooling that took place, resulting in glaciation and also loss of the habitat that led to the second mass extinction, that is during the late Devonian period. All right. Then came the Permian Triassic extinction during 252 million years ago. It was the deadliest extinction. 96% of the complete life perished. And during this point of time, the scientists, they think that the volcanic activity which was there in Siberia, it put lots of carbon dioxide in the atmosphere. Also, because it is a greenhouse gas, so that led to the what it led to? It led to the carbon dioxide, led to the formation of such bacteria which uses carbon dioxide for their survival, and also it led to production of methane, which is again a greenhouse gas. So large quantity of carbon dioxide and methane that led to the global warming, and ultimately the ocean and the rain also became acidic, that led to the extinction during Permian Triassic period at 252 million years ago. Then again came the Triassic Jurassic extinction during the Cretaceous period. So it was about 200 million years ago. During this period of time, what happened was, because of the volcanic eruption again, it resulted into the heat release that was trapped within the inside. Also, it acidified the oceans that led to the mass extinction. Also, over here, another theory is that a comet or asteroid may have impacted the Earth. And due to that asteroid or comet impaction, that led to the mass extinction. During this point of time also, during Triassic Jurassic period, we lost about 80% of the life form. Then came the last extinction in the form of Cretaceous Paleogene extinction about 66 million years ago. So it wiped out the dinosaurs. With the dinosaurs, 60 to 76% of all the life forms also vanished from the earth. And here the widely accepted theory is of the asteroid impact. There was asteroid that landed in the Yucatan Peninsula in Mexico, and then it killed the dinosaurs. This impact, it had resulted into enormous amount of debris that was thrown into the atmosphere. That resulted into cooling of the atmosphere, and again it led to local fires, earthquakes, tsunamis, and acid rain that led to the extinction of the dinosaurs. So these are the 5 major mass extinctions that have happened up to today. This is the 5. These are the 5. We have Ordovician Silurian extinction, late Devonian extinction, then Permian Triassic extinction, Triassic Jurassic extinction, and Cretaceous Paleogene extinction. These 5 extinctions have happened today, up to today. However, the next extinction, this has yet to happen. This has not happened, or we can say this is still happening. This is yet to happen, and it started about 11,700 years ago. Holocene extinction, and this will be primarily derived by the human activities. All right, by the human activities. We are using the resources without any unsustainably. We are using the resources, and that will cause this extinction. So in total, there had been 5 mass extinctions and 5 ice ages that happened on the earth right from the formation of the earth. All right, any doubts up to now? Any doubts, anyone? Clear. Okay, that's nice, Sonali. Everybody else? All right, so that is how our earth came into being, and also the life form existed on the earth right from the starting of the earth. Now, let's talk about the formation of the different layers on the earth. So what happened and how the different layers on the earth were formed. Let's talk about the lithosphere first. Lithosphere, or the solid sphere on which we are there. The uppermost layer of the earth. So earth was volatile in the in the earlier stages, in the primordial stages. So earth was in a volatile state. It was completely molten. However, what happened was that as the density was increasing, the inner temperature also increased. That led to gravitational differentiation. This gravitational differentiation, it occurred on the basis of densities that led to iron catastrophe that we have studied. Right now, heavier sinks at the core, the heavier metals or the iron, it sank at the core, and the lighter metals or the lighter elements move towards the surface. With the passage of time, the layers, they solidified and condensed and formed the outer layer, that is the crust, which is in solid form. Later on, after the formation of the moon, when the Theia impacted the earth temperature again moved upwards. Again, there was differentiation on the basis of densities that led to formation of the 3 layers of the earth: crust, mantle, as well as core, which is divided into inner core and the outer core. That is how the lithosphere came into being. In the same manner, when we talk about the atmosphere, so in the earlier period of time, the atmosphere did not had oxygen. There was no oxygen in the atmosphere, and solar wind, because earth is closer to the sun. So because of the solar winds, there was loss of the primordial atmosphere. In this primordial atmosphere, there was nitrogen, there was methane, there was carbon dioxide, and when there was loss of this primordial atmosphere, there was no oxygen at this point of time. So the earth cooled down. As the earth was cooling down, the interior gases and water vapors were released. That resulted into formation of the early atmosphere, and this early atmosphere had water vapor, carbon dioxide, methane, ammonia, and there was very less free oxygen in this early atmosphere. Then there was degassing. It is the process through which the gases were outpouring from the interior. From the interior, because of the cooling of the earth, the gases were coming outside. and there was continuous volcanic eruption as well that result into the formation of water vapors and gases into the atmosphere. That resulted into present atmosphere, and at present in our atmosphere we have nitrogen, which is a prominent gas, followed by oxygen, and then the rest gases they follow. Even in the formation of the hydrosphere, as the earth was cooling down, water vapor started condensing, atmospheric carbon dioxide, it resulted into the acidic rain. It dissolved in the rain and also further decreased the temperature of the earth. So as the earth's temperature decreased, more condensation happened, more rainfall. This rainfall was collected in the depressions, various depressions, and later on this resulted into formation of the oceans, and that is how we had the evolution of the hydrosphere. So in this manner, the three major sphere of the earth, that is lithosphere, atmosphere and the hydrosphere, came into being. All right, clear everyone how the earth evolved and originated? Any doubts up to now? Then we will move to formation and interior of the earth. Okay, Sagar. All right, very good. Okay, no doubts. So let's move to the next topic of today, that is formation and interior of the earth. How our earth got formed and how the interior of the earth is at present. Now, it is very important to study the formation and interior of the earth because we'll be studying geomorphology. When we study geomorphology, it becomes very important to study Earth's interior. Because when we study Earth's interior, we are able to understand the Earth's surface. What is Earth's surface, how it has been formed. Also, we understand the geophysical phenomena, whether it is volcanism, whether it is earthquakes, or the different geophysical phenomena that we see on the Earth's surface, and also we understand the Earth's magnetic field. How do we have the magnetic field, or the how magnetic field impacts the Earth? Also, when we study the Earth's interior, it becomes essential to understand the internal structure of various solar system objects, because all the solar system, now we know from the most accepted theory, it started or it was formed from the solar nebula. So solar nebula is the source of the complete solar system, and the way the earth has been formed, in the same manner the different terrestrial planets have been formed. All right, so it is important to understand the internal structure of various solar system objects. It is important to study the Earth's interior so that we can understand the evolution and present composition of our atmosphere. Also, when we know about the Earth's interior, it is important for the mineral exploration. We know where we will find the different minerals scattered on the Earth's surface. So that is why it is important to study the Earth's interior. Now, there are different processes on the Earth's surface which mold or which changes the structure of the Earth. These processes can be defined or they can be clubbed into two different factors, that is endogenous process. What is endogenous? Which happens inside, or those that occur or they are created under the Earth's surface. Those processes are called as endogenous process, which are happening inside the Earth. They are not on the surface of the Earth. They are happening inside the Earth's surface, and those processes are called as the endogenous processes. All right. And then there is exogenous processes. The exogenous processes are basically which occur on or near the surface of the Earth. So in the endogenous processes, we have different processes like folding, as well as we have the upliftment and the downward movement of the Earth's surface. And when we talk about the exogenous process, we have weathering and erosion, which shapes our earth. So these are the two processes which shapes or they are responsible for continuously shaping the earth's surface. Now, when we talk about the interior of the earth, so we have different evidences, and these evidences can be clubbed into direct evidences and the indirect evidences. You must be able to differentiate between both of them, because sometimes in your examination, the question has been asked that which of the following is not a direct evidence or not an indirect evidence about the information on the surface of the or interior of the earth's surface. The direct evidences are those evidences which can be or which we can actually directly we can see that what impact they are creating, or we can directly analyze those evidences. Those evidences are basically the direct evidences. In the direct evidences, we have study of mines. There are different mines that have been created or they have been formed for the exploration and also for the various mines have been constructed for the exploration of the different minerals on the surface of the earth. So the study of mines, as we go inside the mines, we notice that there is increase in temperature. We notice the different densities of the minerals, and that is why, because we can directly see those changes when we are going inside the mines, so that gives us the direct evidence. Then the study of lava as well, because the lava is pouring out from the interior of the earth. The lava is coming out from the interior of the earth. So lava gives us the idea that there is at least one layer which is down the earth's surface, which would be in molten state, because lava comes out in molten state. Then the study of rocks as well, the rocks which are found on the surface of the earth, and even those rocks which are thrown out from the volcanic eruption. So by the study of rocks, we come to know about the different composition, whether it is chemical composition or the physical composition of different rocks, and these three are the direct evidences. Please note, these three are included in the direct evidences about the sources of information about internal structure of the earth. Then there are indirect evidences as well. In the indirect evidences, we have rate of change of pressure and temperature. As we are going down from the surface towards the interior of the earth, because of the overlying rocks that are there, the pressure will keep on increasing, because the overlying rocks, they will create or they will have more pressure on the underlying rocks. So of course, when we are moving down towards the center of the earth, there would be increase in pressure, as well as this pressure will increase the temperature as well. And in the interior of the earth, we have different, primordial heat is there, the heat that is remnant when the earth was formed, it is still there at the core. We have primordial heat. We have nuclear materials which are found inside the earth's surface. They also increase the temperature of the earth as we go deep inside the earth. Then there is gravitational anomaly and magnetic variation that can be seen on the various rocks. Seismicity or the earthquake also provides us the evidences, and also the meteors, the study of meteors as well. So they all provide us with the indirect knowledge that there are different structure or different layers which could be found on the interior of the earth. Like for example, I told you that the study of mines gives us the direct evidences. So when we talk about the mines, mines have a particular disadvantage. We cannot go deep up to, beyond a certain certain point of depth. The deepest mine is Puneng gold mine, which is located in South Africa. And the second deepest mine is Tautona gold mine. It is also there in South Africa. However, after a certain depth, we cannot move deep inside the earth and we cannot drill inside the earth, because of course what happens is the temperature increases. So we cannot see very deep inside the earth through mining processes. Also, as we are talking about the indirect sources of evidences, the density will increase as we are traveling from crust to the inner core. The crust has a density of 2.8 gram per meter cube. However, as we move deep inside, the upper mantle has density of 4.6 gram per meter cube, and then the density increases to 13 gram per meter cube when we move to the inner core. So the density is increasing, and as the density is increasing, again it is very important to note that the temperature and the pressure also keeps on increasing. And that gives us indirect source or indirect information that because of the different densities, the rocks would be different, the layers would be found different when we have different densities which are there. Along with this, we have meteors, gravitation, magnetic field anomaly, seismic waves, or the earthquake that gives us indirect information about the interior of the Earth's surface. All right. Now, out of all these sources of information, the most important, sorry, the most important source about the interior structure of the earth is seismic waves. What are the seismic waves? These are the earthquake waves which are produced when earthquake happens. All right. These seismic waves are of two different types. We have two different types of seismic waves, that is, we have body waves. These are the waves, they travel only through the Earth's internal structure or in the Earth's internal layers. They never come on the surface of the Earth. And they are of two types, that is P waves or primary waves and S wave or secondary wave. Then we have surface waves also, and they can move only along the surface of the Earth. They are found only on the surface of the earth. So we have two different types of seismic waves, body waves, P and S wave, and surface wave, which we will study in a different session. And they are basically love waves and relay waves. So when we talk about the internal structure of the earth, it is very important that the body waves, it is the body waves that gives us an idea about the internal layers of the earth. Now, P waves or primary waves, they are longitudinal waves. They are longitudinal in nature and they are similar to sound waves. That is, what happens here is that the particles vibrate to and fro, or they vibrate in the form of compression and then they move along. So that is how longitudinal wave they function. So they are just similar to sound waves, and also they are the fastest amongst the seismic waves. They are least destructive. They are least destructive. Why they are least destructive? Because not, they are not what? They are not surface waves. See, all the body waves will be not destructive. They are not surface wave, and that is why they are least destructive, both P and S waves. Because the destruction happens where? The destruction happens on the surface of the earth. Destruction is of life and property. The life and property exist on the surface of the earth. So because these waves are not surface waves, therefore they are least destructive, and the P wave can travel in all mediums, whether it is solid, liquid or gases, although the speed will be maximum in the solids followed by liquids and gases. They are also called as longitudinal wave or compressional wave or the pressure waves. These are the three different names of the P waves. Then we have the S waves. S wave or secondary wave are transverse in nature. Transverse wave just like a sine wave. Alright, you can see over here, this is a sine wave. So it is just like a sine wave, or you can say like a light wave. Light wave also is transverse in nature. So their propagation is similar to ripples that happens on the surface of water. They have slightly higher destructive power, but they actually do not cause destruction. Please remember, power and actual cause are two different things. P has the least destructive power. Then S has higher destructive power. But actually, P and S wave, they actually do not cause destruction because they are not surface waves. The S wave, they cannot pass through fluids, that is through liquids and gases. They can only pass through the solids. They can only pass through solid medium. So these are the nature of the two waves that we have, that is P and S wave. Now we have the other waves as well, that is we have the surface waves. And when we talk about the surface waves, so in surface waves we have love waves and we have Rayleigh waves. All the destruction is caused by the surface waves. All right. Now when we talk about the internal structure of the earth, so in the internal structure of the earth, we now know that we had the three different layers that are there. Majorly, three different layers are there: crust, mantle, and core. But the earliest, you can say, uh, earliest differentiation or the earliest internal structure layer was given by Edward Suez. Edward Suez gave three different layers, and those three different layers were Sial, Sima, as well as Nife. Now, the crust has average density of 2.8 gram per centimeter cube, and its thickness varies from 8 kilometer under oceans to as much as 32 kilometers under continents, because the continents will have more width. All right, the continents will have more width as compared to oceans. So oceanic crust is thinner. It is about 8 kilometers, and the continental crust would be more, that is up to or as much as 32 kilometers, and it contains granitic and mafic silicate rocks. That is that the density. See, please remember this. This is very important. When we are talking about the crust, we can define crust as, or we can have two different type of crust. We can have continental crust. There are continents, and we can have oceanic crust. The oceanic crust is thinner. It is thinner as compared to the continental crust, but it is denser. It is denser. The oceanic crust is made up of more dense material. At the same time, the continental crust is thicker. It has more thickness, but at the same time, it is made up of light materials, that is, it is less dense as compared to the oceanic crust. Alright, that is why when we will be talking about the plate tectonics, I will tell you that when we have continental and oceanic crust, it is always the oceanic crust that moves downwards from the continental crust. Why? Because the oceanic crust are heavy, they are denser. Please remember this, because this, on the basis of this concept, various questions has been asked in the UPSC examination. Then comes the mantle. Mantle contains ultramafic silicates, right? It is more heavier, and the density is about 4.6 gram per centimeter cube. Then comes the core. Core consists of mainly iron, nickel, and as well as sulfur. And in the core, the density will increase, and it will reach up to 13.6 gram per centimeter cube at the center of the earth. So when we talk about the structure of the earth, that is how the structure of the earth or the internal structure of the earth has been arranged. Now, on the basis of the structure of the earth, these are the layers. But when we talk about the structure of the earth in the form of the you can say chemical composition, or you can say physical composition. So we have lithosphere. Lithosphere is the first layer that is rigid, and it consists of crust as well as upper mantle. This is actually the solid sphere or the solid layer of the earth on which, that is the topmost layer on which all the continents and oceans, they are there. Then comes beneath this is the asthenosphere, which is partially molten. It is partially molten, or you can say it deforms fluidly like plastic under pressure. And it is also part of the upper mantle. It is below the lithosphere. It is also part of upper mantle. Then comes the lower mantle. The lower mantle is basically more rigid. It is solid than asthenosphere, and it is because of the pressure of the overlying rocks. Then comes the outer core, which is in liquid, and also the inner core. So when we talk about the physical layers or the physical properties of the layers, we could have 5 different layers: lithosphere, asthenosphere, lower mantle, outer core, and the inner core. But when we talk about the internal structure of the earth, we have 3 major layers, that is crust, mantle, and core. Now, there are various discontinuities as well, which occurs as we go down inside the earth's surface. What are the discontinuities? How can you define discontinuity? Basically, discontinuity means, or as the name suggests, there is some break in the continuity. That is what discontinuity means. So, discontinuities are nothing but they are the layers which mark changes in densities as we move downwards in the internal structure of the earth. So there would be different regions. I told you, as we are moving inside the earth crust, the density will keep on changing and the density will increase. So as the density is increasing, there would be a zone of separation or discontinuity, where what will happen? That the changes will occur. The densities will increase, and those layers are basically called as discontinuity. These discontinuities have been named after the scientists or the geographers who have identified these discontinuities. The first discontinuity happens between the crust, between the upper crust and the lower crust, and this is called as Conrad discontinuity. It is called as Conrad discontinuity. It is between crust. Then between crust and the mantle, between crust and mantle, we have Mohorovičić or Moho discontinuity. Then between upper mantle and lower mantle, we have Repeti discontinuity. Then between lower mantle and outer core, or we can say between mantle and core, we have Gutenberg or Richard Gutenberg discontinuity, and then we have Lehman discontinuity, that is there between outer core and the inner core. So all these, they signify the changing of densities between different regions or between different layers. Now, how do we come, or why I told you that the seismic waves are very important to know about the internal structure of the earth. And that is why, that is how, because when I told you about the body waves, that is P wave and the S wave, they follow a pattern. The S wave, they do not get inside the liquid layer. So when we measure the S wave after the earthquake originates, so we have seen the S wave pattern, and the S wave cannot be seen between 103 degrees to 103 degrees. Between 103 degrees to 103 degrees from the epicenter. That means that they are not going inside the outer core. Now, outer core is in liquid form. Why or how do we know about that? Because of the S wave pattern. Because S wave, it creates a shadow zone between 103 to 103 degrees, and that is why we know that the S wave, which travels only through solids, it goes only through solids, it travels only through solids. So that is how we come to know about that the internally the inner core, the outer core is in liquid form. But at the same way, the P wave patterns you can see over here that the P wave are not seen between 103 to 150 degrees only. That means the P wave shadow zone is lesser as compared to the S wave shadow zone. And this happens because when the P wave is moving inside the Earth's surface, there is refraction, and that the refraction leads to bending of those waves. So there is only bending of the waves. What is refraction? The bending of rays when they go from one medium to the another medium. That is what we call as refraction. So because of that refraction, the P waves are not seen on the seismograph only between 103 to 150 degrees, and that is the P wave shadow zone. So P wave shadow zone and S wave shadow zone. You can see that between both of them, S wave shadow zone is larger as compared to that of the P wave shadow zone. All right. Now, when we talk about the internal structure of the Earth, like I said, that the internal structure of the Earth is comprised of three different layers: crust, mantle, and core. The crust is only one layer. Mantle can be divided into two layers. That is, we have upper mantle and the lower mantle. And in the same manner, the core can also be divided into outer core and the inner core. All right. Now, the first layer, that is the crust. When we talk about the crust, it is the outermost layer of the earth. It is the outermost layer of the earth, and it makes up to only 0.5 to 1% of the earth's volume. That is, it is very thin layer. It is very thin layer, and it is also less than 1% of the earth's mass. Its density or its thickness, it measures or it moves from 8 to 32 kilometers. It is 5 to 30 kilometers thickness in the case of oceanic crust. And when we talk about the continental crust, it could be 50 to 70 kilometer in the case of continental crust. The density, average density is 2.7 gram per centimeter cube, which ranges from 2.7, the outer crust that is there. All right, we have the outer crust or the upper crust. So outer crust will have density of 2.6 to 2.7 gram per centimeter cube. However, when we move inside the inner crust, the density increases. The density, it reaches 3.0 to 3.2 gram per centimeter cube. And that is why we have in between the crust, we have Conrad discontinuity, which marks the changing in the density of the rocks at that point of time. The complete crust is covered by the sedimentary material because there had been weathering and erosion, and that is why it led to the formation of the upper layer or the sedimentary layer that could be found on the surface of the crust. The most abundant elements of the earth crust are oxygen, then comes silicon, and then aluminium. Then comes iron and the sodium. So the most abundant elements of the earth crust is oxygen, silicon, and aluminium. When we are talking about the continents, I told you that the continents are basically, they are lighter or they are formed by lighter rocks. The continents are formed by lighter components or lighter silicates, that is Cl, or you can say silica and aluminium. That is why the continents are lighter or they are less denser. But at the same time, oceans have heavy silicates, SEMA, or silica and magnesium. That is SEMA. So the oceans are mainly composed of SEMA and the continents are composed of Cl. That were the first two layers that were given by the Edward Swiss. The continental crust is also composed of sodium, potassium, aluminium silicate rocks like granite, and the oceanic crust is mainly composed of rocks like basalt. Or you can say that the continental crust is less lighter, or sorry, it is less denser as compared to the oceanic crust, which is more dense because it has iron, magnesium silicate, igneous rocks or basalt rocks which are found here. And that is why oceanic crust will move downwards the continental crust when we will study the plate tectonics theory. Another thing that has to be kept in mind that the continents are far wider as compared to the oceanic crust. Then comes the lithosphere. Lithosphere is actually the solid sphere, the solid part that we see. The thickness varies from 10 to 100 kilometers, or you can say that they form the lithospheric plates on which the complete continents and the oceans they are there. It is made by the crust and the upper part of the mantle or upper mantle which is solid in state. The tectonic plates are comprised of these lithosphere, and these lithosphere, the complete lithosphere has been divided into different segments which we call as the tectonic plates. These tectonic plates are continuously in motion. We will study the complete plate tectonics. It is very important theory for understanding the complete geomorphology. So the complete crust or the complete lithosphere is divided into segments, and these segments are called as tectonic plates. These tectonic plates are continuously in motion, which gives rise to the different geomorphic phenomena, whether it is volcanoes, whether it is the earthquake, or whether it is the formation of mountains or the orogeny. Also over here you will find the primordial heat, the leftover heat after the Earth's formation, and there is radioactive decay of uranium, thorium and potassium as well in the mantle. This primordial heat and the radioactive decay is actually the responsible force behind movement of these tectonic plates. Then comes the mantle. Beneath the crust, we have mantle. Mantle is 83% of the Earth's volume and it is 67% of the Earth's mass. The density of the upper mantle, it can range from 2.9 gram per centimeter cube to 3.3 gram per centimeter cube, while the density of lower mantle increases and it is from 3.3 gram per centimeter cube to 5.7 gram per centimeter cube. Here you will find the silicate minerals and will be composed of mainly the iron silicate and the magnesium silicate, and over here you will find oxygen, silicon and magnesium which will be majorly found here. Crust has oxygen, silicon and aluminium. Crust's main elements are, what are there? Oxygen, silicon and aluminium. OSA you can say. Alright, so we have more of oxygen, silicon and aluminium here. However, when we talk about the mantle, we have silicon and magnesium prominently over here along with the oxygen, because silicate rocks are basically, what is silica? Silica is nothing but SiO2. So when we say silicate rocks, it contains silicon and oxygen. That is the formula of silica. So silica and silicon and also oxygen will be there, and then magnesium will also be here. Then beneath the lithosphere is asthenosphere. What is asthenosphere? It is basically a solid layer. You must have seen over here when I was talking about the shadow zones. So in shadow zones, if the asthenosphere is basically a liquid, so the S waves would not pass through the asthenosphere as well, but the S wave passes through the asthenosphere. That means that asthenosphere is actually not liquid, it is solid, but it behaves like liquid. It behaves like liquid. So asthenosphere is actually solid which behaves like liquid. Why it behaves like liquid? It behaves like liquid because of the pressure of the overlying rock. It is just below the lithosphere and it is from 100 to 350 kilometers. It is highly viscous, mechanically weak and ductile. That is why it behaves like liquid and it aids in plate tectonic movement. The plates which move, they move on the asthenosphere. And it also leads to isostatic adjustments. Now, what is isostatic adjustment or what is isostasy? This is a new word that you must have heard today. Now, when we are talking about isostatic adjustment, it is inherent, you can say, property or characteristic of our earth that it balances itself. It balances itself. Like for example, the mountains, they are getting eroded. So when the mountains are getting eroded, what is happening? That the debris is getting fallen into the oceans or the sea. So they are coming, the height is decreasing. At the same time, the depth of the oceans and the sea, it is moving upwards. So our earth has an inherent characteristic of making changes or of balancing itself. That balancing act of the earth is called as isostatic adjustment. The asthenosphere is the major source or main source of the magma. Whenever we have the volcanic eruption, the magma comes from the asthenosphere. Then beneath the mantle comes the outer core. The outer core is basically composed of iron as well as nickel. We have iron and nickel, but there is not enough pressure. So because there is not enough pressure, so it behaves or it is in liquid condition. It is not solid, it is a liquid layer. Outer core is in liquid state, it is a liquid layer, and we come to know about this because the S wave do not passes through the outer core. The density again, it will increase because here we have heavier metals like the iron and nickel. So density ranges from 9.9 gram per centimeter cube to 12.2 gram per centimeter cube, and there is convection in the outer core along with the Coriolis effect that gives to the Earth's magnetic field, or that results into dynamo effect. I will explain what is a dynamo effect and how dynamo effect leads to the Earth's magnetism. Then comes the inner core. Inner core is mainly comprised of the iron itself, and there is some nickel as well. It rotates slightly faster because it is in solid form and the density ranges from 12.6 to 13 gram per centimeter cube. It is just 16% of the Earth's volume, but 33% of the Earth's mass. That means the density is very high. Density is actually, what is density? It is mass upon volume, right? So the density will be very high when we talk about the inner core, and because there is lots of pressure of the overlying rocks that prevents it from becoming liquid, and that is how we have the solid core or the solid inner core. So over here you can see the internal structure of the earth that we have. This is the internal structure of the earth. Just okay. So we have the crust that is here. The crust is actually from 0 to 32 kilometers thick. All right. But when we talk about lithosphere, lithosphere is up to 100 kilometer thick. So we have crust that ranges from 5 to 30 kilometers. And 0 to 100 kilometer, we have lithosphere. Lithosphere, that is the solid structure of the upper part of the earth. All right, then comes the mantle. The mantle, the upper part of the mantle is aligned with the lithosphere. Then comes beneath it, we have the asthenosphere, which is the molten or it is the plastic state. It is in plastic state and helps in the movement of the tectonic plates. Then comes the core, that is we have the outer core which is liquid, and the solid core which is solid. Inner core which is solid. Then comes we have the center of the earth. So center of the earth is at about 6371 kilometers. At the same time, we have different discontinuities which we have discussed. We have Conrad discontinuity, which happens between the crust, between the upper crust and the lower crust. Then we have Mohorovičić or Moho discontinuity. The complete name is Mohorovičić discontinuity. You may find it. It is between crust and the mantle. Then between mantle, we have the Rapidi discontinuity between upper mantle and lower mantle. Then we have Gutenberg or Wiechert-Gutenberg discontinuity. We have Wiechert-Gutenberg, or simply it is called as Gutenberg discontinuity, that is between mantle and core. And then we have Lehman discontinuity, that is between core, between outer core and the inner core. Now, the internal structure is clear to everyone. Any doubts so far? Is it clear to everyone? Internal structure, crust, mantle and the core. Okay, great. Ritik and Sonali. Now, we have different layers, and in the same manner, we have different elements which are present. Is asthenosphere considered as part of upper mantle? Yes, it is part of upper mantle. It is actually not considered, it is part of upper mantle. Asthenosphere it is part of upper mantle. Okay, Raj? Lithosphere comprises of crust and part of upper mantle, and beneath lithosphere we have asthenosphere. So asthenosphere is up to 350 kilometers from the surface. So it is up to 350 kilometers, 100 to 350. So that part comes under or it is the part of upper mantle. Now, as we have seen that we have the different layers of the internal structure of the earth. Now, we have different elements as well which you can find in the different layers. This is very important. This question has been asked in examination various times. You have to remember this. We have most abundant elements of the Earth's crust. Crust means only the uppermost layer. Crust means only the uppermost layer. So in the uppermost, you will find oxygen, which is the prominent element. Then we have silicon, because both of them, they make silica. And in silica, SiO2. O2, we have two molecules, and for silica, we have single molecule. That is why oxygen is highest in the earth crust. Then comes silica or silicon. Then we have aluminium. And then we have iron and calcium, followed by sodium, potassium and magnesium. But at the same time, when we see the most abundant elements of the earth, so when we are talking about the earth means all three layers. When all three layers are combined together, so by the percentage of weight, we have iron, that is maximum, followed by oxygen, then silicon, and then magnesium. And later on, nickel, sulfur, and titanium, etc. So when we are talking about the earth crust, it is oxygen, silicon, aluminium, iron, and calcium. Okay. And when we are talking about most abundant elements of the earth, so it is iron, followed by oxygen, silicon, magnesium, and nickel. Please remember both of them separately, because the question could be asked about the most abundant element of the earth crust, or it could be asked about most abundant element of the earth. You do not have to remember the percentage by weight, but you have to remember the order, the correct order of their abundance. Right. Now, what happens and how we have the magnetic field that emerges, or the magnetic field, it comes into role play, how the Earth's magnetic field is formed. So I don't know whether you have, in physics, I guess in 11th or in 10th, we have this dynamo. There is even a project that you have to make of dynamo. Now, how dynamo works? Dynamo, you must have seen generators which generate the electricity. Now, what happens in generators? In generators, actually nothing happens. We use dynamo to produce the electricity. Now, what is a dynamo? How you create a dynamo? In dynamo, we have two different layers, circular layers, all right, or cylindrical layers. So, there is a layer, inner layer, and there is outer layer. We have two different layers, inner layer and outer layer. The outer layer is composed of magnets. There are different magnets that are laid in the outer layer. And in the inner layer, there is a electrical wiring that is there. Electrical wire, which is basically rounded off on the coil. It is a coil of electrical wire. Now, how this dynamo produces electricity? The coil that is inside, it is rotated very fast inside that outer layer of magnets. Now, what happens is that results into formation of electromagnetic field, and because those electrical wires, because of those electrical wires, what happens is that the electricity is produced. That is how a dynamo works. All right. In generator, the same thing is used. What happens is that there are a coil, and within the coil there is a magnet. Magnet is rotated very fast so that the electricity can be generated using that dynamo. The same thing happens with the Earth's internal structure as well. What happens is that we have outer core which is in liquid form. It is in liquid form, and then we have the inner core which is actually solid. Now, what happens because of the differences of being solid and liquid, their rotational velocities are different. The inner core, because being solid, inner core rotates faster. Inner core rotates faster, and inner core has more of iron as compared to nickel. Now, this inner core and the outer core, it functions like a dynamo. We have inner core that is rotating faster in a chamber of the iron or of the outer core. Now, because this iron ore, the inner core is rotating faster, this results into formation of the same electromagnetic field. However, here electricity is not generated, but electricity also, or the electromagnetic field also, have a magnetic field of its own. So magnetic field gets generated, and this magnetic field, due to this dynamo impact or dynamo effect, this is called as dynamo effect or dynamo theory. So this dynamo effect leads to the formation of the magnetic fields, and that results into Earth's magnetism. Clear everyone how this Earth's magnetism is getting formed, or why we have magnetic field of the Earth? Because of the core, because inner core rotates faster inside the outer core. That results into formation of electromagnetic field. We do not have electricity over here. We cannot have the electricity. We cannot, although if you will put two wires over here, we can have so much of electricity that we will not require any other method or any other means to produce electricity. But we cannot go up to so much down inside the core. So what happens is that instead of electricity, we have the magnetic field which gets generated, and this convection currents, or this, the Coriolis effect along with the dynamo effect, it leads to formation of the magnetism, Earth's magnetism. Okay, clear? Clear everyone? Now, when we see that why or how this magnetic field impacts our Earth. So, yesterday also I have told you that there are solar winds. The solar winds are nothing but they are the charged particles. They are the charged particles which emanates or which originates from the sun's atmosphere. Now these solar wind particles, they pushes the Earth's magnetosphere. We have the Earth's magnetosphere when we have the photons or the charged particles which are moving towards the Earth's magnetosphere will have over here bow shock. Bow shock is towards the sun. Then also we'll have the magnetosheath and the Earth's magnetic field. We also have Van Allen belts. These are Van Allen belts or Van Allen radiation belts which were seen by Van Allen. There are two different Van Allen belts. I will tell you about them. Now over here you can see that these are the magnetic field. The photons, they interact with this magnetic field that gets or that generates the auroras. We have different auroras that are formed. Now we have two different Van Allen belts. We have Van Allen A belt or Van Allen A and B belt. We have A belt which is inside, interior or inner belt. Inner belt is about 100,000 to 8,000 miles above. All right, from the surface of the Earth. And over here you will find that electrons would be there. And then we have outer belt that is up to 12,000 to 25,000 miles. And over here you will find mostly protons which will be trapped here. Now, because of these Van Allen belts which have electrons and protons, and also we have the solar winds, when they all combine with the Earth's magnetosphere, that leads to formation of the northern lights or what we call as the auroras that have been formed. So over here you can see that when we talk about the magnetic field of the Earth, solar wind, it comes to the atmosphere and it moves with or it interacts with the magnetic field. It interacts with the atmosphere as well. When we talk about over here, you can see that the Earth, when we talk about the Mercury and Venus, they do not have the magnetic field. On the Earth, what happens? The solar wind is mostly deflected by our magnetic field. Solar wind is mostly deflected by the magnetosheath that is there or magnetic field. But sometimes when the solar wind are intense, some of it comes inside, and once it is near the Earth's space. So at that point of time, it triggers the aurora near the poles. All right. When we talk about the moon, because its atmosphere is thin, the solar wind hits the moon's surface directly. And there is very less deflection of the solar wind or the solar particles. And the moon's magnetic field is not that much high because its size is very small. However, when we are talking about Jupiter, Jupiter has the highest magnetic field in our solar system. Its magnetic field is similar to that of Earth, but it is very, very large. It is very large, and the highest magnetic field on the surface or on the in the solar system, it can be found on Jupiter. All right, and this creates a bubble that directs the solar wind to stream around that of the Jupiter. All right. Now, when we are talking about the magnetism, over here, you have to note that the Earth's geographical north and the magnetic north are different. We have different magnetic north and the geographical north. So over here, you can see that there is deviation of 11 degrees from the geographical north pole to the geomagnetic north pole. All right. And also, if you'll see that the geographical south pole and the geomagnetic south pole would be different. So when you see a compass actually do not point towards the actual north pole and south pole. It points you towards the geomagnetic north pole and geomagnetic south pole. Where is the geomagnetic north pole located? It is located at 86 degree and 50 minutes north. Please note that you will never write, I don't know, I was, in a hurry. You will never write degrees like this, but you will write it like this. Okay. The point should not be used whenever you are writing degrees. It should be written as 86 degree 50 minutes north and 164 degree and 4 minutes east. So that is the location of the geographical North Pole. It is north of Ellesmere Island in northern Canada, and it is shifting towards Siberia. It shifts about 10 km per year. And the geomagnetic North Pole is located at 64 degree and 7 minutes south and 135 degree and 88 minutes east. It is off the coast of Antarctica and outside the Antarctic Circle. So the geomagnetic South Pole is in Antarctica, but the geomagnetic North Pole is outside the Antarctic Circle. So you can understand that the geomagnetic and the geographic North Pole and South Pole would be always different, or they will be always, they will not be superimposed with each other. All right. Now, I told you whenever you are writing, you have to write it like this because you can say that the minutes, we have seconds, we have minutes and degrees. So degrees are basically the multiples of 60. All right. We have 60 seconds, that's 60 minutes, and then we have degrees. All right. So the basic unit of degrees is 60. But when we are using point system, it is decimal system which is based on 10 as a base number. So you cannot write degrees in points. You have to write it in degrees, minutes and seconds. Or you can write it in a, what you call it as with the fractions as well. You can write it with fraction. Like for example, we can write it like this, 82.5 degree east, or you can write it like this, 82 degree and half means 30. So 30 minutes east. You can write the degrees like only this. You will never write degrees like 82.50 degree. You will not write this. This is incorrect way of writing degrees. All right. Now, let's understand some of the questions which were asked before in the prelims. The first question is, or before moving to this question, let me tell you one more thing about the magnetic poles. We have the magnetic poles over here. There is also a term that is called as geomagnetic reversal. There is geomagnetic reversal as well. I have told you, I guess, yesterday as well when we were studying the sunspot. Geomagnetic reversal is actually linked to sunspot. Whenever the Earth's magnetic field goes into waning phase, that means it becomes less. And there is highest sunspot activity that leads to geomagnetic reversal. What happens during geomagnetic reversal? The geomagnetic North Pole becomes the South Pole and the geomagnetic South Pole becomes the North Pole. But you will never experience it, or you will never be able to know that there had been a geomagnetic reversal. Why so? Because the compass will still be pointing towards north and south. So what happens is that during the geomagnetic reversal, the North Pole becomes south. So this compass will still be pointing in north and south direction. So you will not be able to understand it until you do a magnetic, complete, the magnetic anomaly, or you can see the different magnetic poles in the rocks, or you study the rocks for their magnetic poles. So until then, you will not be able to find out whether they had been a geomagnetic reversal or not. Okay, so that is what we call as geomagnetic reversal. Now we have the first question over here. The axis of Earth's magnetic field is inclined at 23.5 to the geographic axis of the Earth. The second, the Earth's magnetic pole in the northern hemisphere is located on the peninsula in northern Canada. And third, the Earth's magnetic equator passes through Thumba in southern India. So over here, you will find such kind of question. The axis of Earth's magnetic field is inclined to 23.5 degree. So What is 23.5 degree? It is the inclination of the Earth's axis. It is not actually the inclination of Earth's magnetic field. Earth's magnetic field is actually inclined to about 11 degrees. So that is why first question is incorrect. Second question is also incorrect. Earth's magnetic pole is in northern hemisphere, located on the peninsula in northern Canada. All right, it's on not peninsula, it's on the Ellesmere Island. There is Ellesmere Island where we have the magnetic north pole located, and only third is correct where the magnetic equator passes through Thumba in the South India, where we had the earliest rocket launch station as well. We had TERL. TERL is located here. All right. TERL is Thumba Equatorial Rocket Launch Station. India's first rocket launch station was constructed here. TERL, Thumba Equatorial Rocket Launch Station. All right. So over here you can see that the axis of Earth's magnetic field is about 11 degrees. It's not 23.5 degree. It is about 11 degrees. And also you can see that the TERL, it passes through the equatorial magnetic equator. The next question over here is, consider the following statements. In a seismograph, P waves are recorded earlier than S waves. Yes, they will be recorded because the P waves travel fastest. They travel fastest among all the seismic waves. In P waves, the individual particles vibrate to and fro. It will be to and fro in the direction of wave propagation, whereas in S wave, the particles vibrate up and down at the right angles to the direction of wave propagation. Again, both of them are correct. Both of them are correct because P waves are what? P waves are just like sound waves, or they are longitudinal waves. So in longitudinal waves, what will happen is the particle vibrate to and fro. And when we talk about S wave, they are transverse wave. So over here, the particles will vibrate at 90 degrees or right angles up and down. So both the statements are correct. We will have the answer as both 1 and 2. So over here you can see P waves are the first waves to be there on the seismograph. Then comes S wave, then the surface waves. Then we have another question over here. Will you share this PDF or do we need to copy what you write on the board? I will share the PDF, Sonali. I have shared the yesterday's PDF also in the group. And today also, just after the class, I'll share the PDF. All right, do not worry. Then we have the another question over here. Consider the following statements. The Earth's magnetic field has reversed every few 100,000 years. All right. So I have told you about geomagnetic reversal. Again, this is true that the Earth's magnetic field, it reverses itself, and this is known as geomagnetic reversal. All right, this is geomagnetic reversal. Then when the Earth was created more than 4,000 million years ago, there was 54% oxygen. I told you initially there was no oxygen, but there was carbon dioxide. All right, there was carbon dioxide. So second statement is incorrect. Then third statement, when living organisms originated, they modified the Earth's atmosphere of the Earth. That is true. That led to formation of oxygen, and oxygen, it then came into the atmosphere. So we have 1 and 3, that is correct. That means answer is C. That is right answer. All right. So initially, we do not had the oxygen. All right, initial atmosphere did not had the oxygen. It had hydrogen, nitrogen, carbon monoxide, carbon dioxide, ammonia, water vapors, methane that were there. With the main composition, we had the carbon dioxide and the nitrogen. All right, now, any doubts, anyone? Any doubts, anyone? You can ask your doubts now. Any doubts in today's session? All right. So that would be all in today's session. We'll meet again tomorrow at the same time, that is at 11 o'clock, and we will discuss the another thing. You are not part of the WhatsApp group. Why you have not joined the WhatsApp group, Raj? There's a WhatsApp group for geography. You have to join that WhatsApp group because I'll be able to share the PDFs only over there. There's a group PMFIS Geography Foundation 2026. We have 45 members that are there. All right. Please join this group. I guess there is, you requested. Do you have this 572 at the end of your mobile? It ends with 572, Raj. The last numbers of your mobile? Okay. All right. Okay, I have approved you. You are not part of the group. Okay, Raj? All right. Any other doubts? Yes, this doc I will share in that group, the foundation group. Yesterday's session also, the notes were shared there. And today's session also, I will share the notes there. NCERT chapters, what to refer for today, sir. So you can refer the internal structure of the earth. All right. I will share a complete NCERT, how you can read the NCERTs, which all NCERTs you can read, and how you can cover the complete setup. Okay, I'll share the complete, the NCERT as well as they are the old NCERTs, but you will find the PDF online as well. So just go through those chapters. If you are covering the NCERT chapters along with this, so please go through it. And also remember that NCERT in NCERT, there are certain things which have been written wrong. Okay, so that also you have to keep in mind. All right. Yes, class material is alone enough, although Sonali. All right, but if you want to refer to other things, like you have the PMFIS study materials that have been provided to you. All right, so PMFIS, the geography books, they are good enough. With my notes, with my class materials, along with those PMFIS materials, if you will go through it, you will find everything. All right, you do not have to read anything else. Okay. All right. All right. So that would be all in today's session. I guess we'll meet again tomorrow at the same time at 11 a.m. and we will cover the next topic. And the next topic for tomorrow would be, it would be just a second, geomorphic movements and plate tectonics. All right. Although what can happen is that I could take another session as well, because I want to explain the plate tectonics over the board, the smart board. So it may happen that I may explain you the plate tectonics on the smart board, and then I may take the other sessions. Or what we can do is we can have a session on smart board for plate tectonics separately. All right. And what we can do is we can have the class movement or the class to go through in the same manner, as so that we do not miss anything, and because everything is linked with each other. So we are in a way, we are not lagging behind, or we do not lag behind. Okay, so we will see, either we'll have the plate tectonics tomorrow, or we will have the another session, that is mountains, types, formation, plateaus, plains, and volcanism as well. All right, so that would be all. Thank you. Bye-bye. Take care. Jai Hind. We'll meet again tomorrow at the same time. Thank you.